In this lecture, I am going to explain about load line analysis. Load line analysis, analysis can be applied for a transistor amplifier connected in any configuration CBC, CC. And in this analysis, we can get through how the transistor act as an amplifier. In this load line analysis, we have topics of operating point and DC and AC load line. So the figure shows the simple representation of a common emitter configuration by providing signals and proper biasing. It is a circuit for CE amplifier. Before going to analyze this CE configuration or CE amplifier circuit, whether it is working for amplifier or not, first we will see that biasing. What is biasing? Biasing means by providing proper supply voltages and proper resistors to transistor configurations such that it will give faithful amplification. The word faithful amplification means here, if you take an amplifier, transistor amplifier, it is an amplifier. If I am giving sinusoidal AC signal, which represents AC input signal or low input signal, a weak signal, this can be given to amplifier circuit. The amplifier circuit is a circuit which can strengthen the input, given input signal, weak input signal, without losing any information, without suppressing either direction, positive and negative direction of this signal. That is called faithful amplification. No clipping some portion on the positive side or some portion on the negative side. Perfectly amplified of the given input signal. The shape of the signal is same, but it is gets strengthened, amplified. This signal is called faithful amplification signal. This circuit which can amplify faithfully. So in order to get faithful amplification, we have to provide proper biasing by providing proper resistors, by providing proper supply voltages at input side and at a output side. So in this case, we have different kinds of biasings. We will see later what different kinds of biasings. Now we will see how to find out the Q point, how to find out the load line and draw the load line. So let us see now first DC load line. What is DC load line? When we take any transistor amplifier, by giving zero input signal and provide a proper biasing to the amplifier, and we'll get a line on the output characteristic. So that line is called DC load line. And what is the purpose of DC load line and a Q point? Here, the main intention to go with this DC load line and a Q point means same amplifier. If you take an amplifier, we know the output characteristics. You know the output characteristic. The output characteristics is the relation between output current and output voltage. Output current and output voltage. So this, suppose the transistor amplifier operated in active region. In order to make this circuit act as an amplifier, you must and should operate in this characteristic active region. So in this active region, when the Q point on the characteristic curve, a point is in the active region, then the signal will amplify faithfully. Suppose this operation of the transistor amplifier is near to saturation region or operated in the saturation region. So in this case, will get suppressed in the O2 cycle. If it is saturation, operated in saturation region, or if it is operated in cutoff region, near to cutoff region or cutoff region, then you will get this kind of portion clipped. This positive portion clipping. This positive portion gets clipped by the point of the circuit operated near to cutoff region. So in this way, when we operated a transistor amplifier near to saturation region, we get some portion of the signal clipped up. And if you operated the transistor near to cutoff or cutoff region, then some other positive cycle clipped off. So in order to get this signal completely allowed and amplified at the output of an amplifier, you must understood that the circuit is operated in active region only. But we hope that we feel that it is operated in active region, but in reality, the circuit never fixed it up in the active region. It may be varied. It may be moves that operating point from active region to some direction. So that because of that, maybe there are different reasons. One of the reason is changing the load and changing the parameters, some temperature sensitive parameters, beta, VBE, and then output current changes, so that this Q point may changes. So then when it is changes, we need to be care about it, and we need to be fixed it at near the center or almost near the center. Don't go to the saturation region and cutoff region. So in order to get faithful amplification, we need to fix that Q point and on the active region only. So in order to get that Q point in the active region, first to find out how to measure that Q point in the active region. So the prerequisite for this Q point is we have load line, we have output characteristics for that particular circuit. When we have output characteristics for that particular circuit, and find out the load line, then in that load line we get that Q point, and that Q point must be careful and provided with this Q point won't move to saturation region and cutoff region. Now we will see that what is the like load line, how to draw the load line. So when the value for the maximum possible collector current is considered, that will be presented in the y-axis. When we take the y-axis, the maximum point on the y-axis can be considered as saturation point, which is called IC sat. IC sat. This point placed across the y-axis, and also as well as when we mark the point on the x-axis, maximum point on the x-axis, the maximum possible collector to emitter voltage is considered. That point will be presented on the x-axis, which is represented as cutoff point, VCE cutoff. VCE cutoff. When line join these 2 points, over the output characteristics, let us take C configuration, we will get output characteristics like this. So in this output characteristics, when we draw the line, join these 2 points, which makes the Q point. A contact, if for example, if you take any point, cross-sectional point here, or not only cross-sectional point, in this curve, you can take anything. So this cross point between output characteristics and load line is called Q point. Q point. Q point is also called operating point and quiescent point or Q point. So this Q point must be maintained in the active region only. So it is actually graphically we can draw this Q point from the mathematical equation from the characteristic graph from the amplifier circuit, we can get the Q point coordinate points. If this load line is drawn only when DC biasing is given to the transistor, but no input signal is applied, then such load line is called DC load line. For this DC load line, absence of AC input signal given to the amplifier circuit. Then what is the load line and corresponding its Q point, which gives the some faithful biasing. Whereas the load line drawn under the conditions when an input signal is along with the DC voltages are applied, such line is called the AC load line. So when after providing the AC input signal, again we can apply the conditions, then we can get the line superimposed with the output characteristic. That line is called AC load line. So now mathematically, how to get these extreme points on the y-axis and extreme point on the x-axis and join together to get the load line. So from the output collector characteristics or output current, output Kirchhoff voltage law we can apply, and then from that equation we can say that transistor VCE is equal to transistor voltage between collector to emitter, VCE is equal to VCC minus ICRC. It is the equation derived from the output characteristics Kirchhoff voltage law. So VC is equal to VCC minus ICRC, just like this one. So when we apply Kirchhoff voltage law to this loop, so one source is there VCC minus current flow in the RC is equal to IC into RC, that's what voltage drop across RC. The potential between collector and emitter is called minus VCE is equal to 0. Algebraic sum of all voltage is equal to 0 in the loop from this point to this point. So this can be rewrite equation VC is equal to VCC minus IC into RC. If RE resistor is there, we can add some more term, one more term, which is nothing but IE minus IE into RE. Here not there is no emitter resistor, we get VC is equal to VCC minus ICRC. From this output Kirchhoff voltage law equation is helpful to find out the load line and Q point. How to find out? To obtain the maximum extreme points on the y-axis and x-axis, substitute one extreme point, substitute one x-axis variable kept 0 and substitute in the equation, in this equation, for example it is 1, and we will get the y-axis point, maximum point, or y-axis point is nothing but saturation point. In the second time, when we substitute y-axis point is 0 and mark the x-axis maximum point, which is called cutoff point on the x-axis. So first we will see that x-axis point 0. We know that x-axis is called output characteristics. One of the parameters is VCE, x-axis point. So it is a graph between IC in milliampere, VCE in volts. So this x-axis point 0. When x-axis point gets 0, the collector current is maximum, which is equal to VCC by RC. So in this equation, substitute VC is equal to 0, and then VCC minus ICRC is equal to 0, then IC is equal to VCC by RC. This is the maximum point on y-axis. This is the maximum point on y-axis. This maximum point. This is called IC sat. IC sat. And then we can get a substitute x-axis point, y-axis point 0. What is y-axis point 0? To obtain the point on the x-axis, substitute y-axis point variable IC is equal to 0. Then collector to emitter voltage gets maximum, which will be equal to VCC. Take the equation VGC is equal to VCC minus RC. Substitute IC is equal to 0. When IC is equal to 0, this term gets 0. Then VC is equal to x-axis variable VC is equal to VCC. That VCC is nothing but supply, collector supply, which may be equal to 10 volts or 20 volts, 12 volts based on the requirements. So when VC is equal to VCC, that will be another point on the x-axis. This gives the point B, which means OB is equal to O nothing but origin. OB is equal to VCC on the collector emitter voltage axis. Okay. So this is a 0. This is the point B. This the point A. This point B nothing but VCC, which is equal to VCC. It's also called VCE cutoff point. VCE cutoff point. So when we join these together, this point is VA and this point is B. Join this together to get load line. So now we have already this output characteristics. So we'll take Q point. What is Q point means? It is the operating point on the x-axis, which is represented by VCQ, where the Q point is presented in the output characteristics, which will make the transistor amplifier gives the faithful amplification. That point is called Q point. So we can refer to as this Q point is in the x-axis coordinate point is VCQ and y-axis coordinate point is ICQ. So we can term it as Q is nothing but ICQ, VCQ. ICQ, VCQ. So here we can find out that Q point for the particular amplifier circuit to get the faithful amplification. Now AC load line. In this AC load line, when the collector current and voltages points on the output characteristics by providing a signal at the input side. In contrast, DC analysis or DC load line, the DC load line which we discussed in previous section, which analyzed the variation of collector current and voltages when AC voltage is applied, is absent, when AC voltage is not applied. When we apply the AC voltage and it gets a load line, which gives the peak to peak voltage or the maximum possible output swing for a given amplifier. If you take the amplifier circuit or simplified amplifier circuit by providing the V input signal and this bias resistor, suppose if it is single resistor, that will be treated as only single resistor like bar B, or if we connecting or some different biasing networks like R1 parallel with R2, then we can take this R1 parallel with R2 and output resistor. If it only single, it has single resistance RC. Otherwise, if it is output is connected to load resistor, that RC is equal to that total resistance is equal to RC parallel RL. You will get a total resistance RC is equal to RC parallel RL. So by considering the resistors and batteries, Then we can consider the input signal and draw the load line, find out the load line from the output Kirchhoff voltage law, and then draw the load line. We will get AC load line. That AC load line, the slope of the AC load line is like this, the green color, as shown in the figure, green color, and DC load line, this one. So when we are providing the signal at input side, then the load line will make changes. So this load line, AC load line, which will gives the swing of positive swing and negative swing of the AC input and output signal. So we can measure this AC load line, measure the whether this complete swing in either direction, positive and negative direction. The cross section point of this two DC load line and AC load line is called Q point here. Now, in order to get that Q point for particular amplifier circuit, we have to provide a proper biasing. So there are different kinds of biasing, which is called different kinds of biasings, which are called fixed bias or base bias and a voltage divided bias. In this subject, which covers fixed bias and voltage divided bias. What is fixed bias connection? Fixed bias means if a transistor amplifier providing a biasing, if providing a biasing at input side, for example, if I am providing an input side biasing, if it is network, take this transistor, base resistor, supply voltage, and RC and supply voltage VCC, and output here. Here it is input, you will get input. If I am providing two batteries, VBB and VCC, these two batteries are fixed to operating input base to emitter voltage must be on. In order to get this transistor on, we must provide a battery or supply to this base terminal, so that this base to emitter voltage must be on greater than 0.7 volts. And this output, in order to operate the output side, we provide VCC. So this fixing of this voltage at input side and output side is called fixed bias connection. So in this basic fixed bias circuit requires two supplies, two different batteries. So why do we need two separate batteries? Why don't we eliminate that two batteries in order to provide a single source? So that idea can be applied here in this fixed biasing, in this fixed bias diagram. So the same base resistor, base terminal having base resistor, this base resistor having different supply voltage, but in this case I'm taking that resistor other end to the collector supply, VCC supply only, so that the VCC voltage applied to base resistor, some voltage drop across the base resistor, the remaining voltage will be available in this base point. That voltage make this transistor gets on, and this voltage passing through the collector and VC emitter terminal, so that it will be also one of the closed loop at the output side. So this idea is called fixed bias, or base bias, base terminal, base resistor bias. In this fixed bias, whether the circuit gives faithful amplification or not. By taking the output characteristics, we can't say that it is operated as an amplifier. So it is need to be find out the load line, find out the Q point for this particular fixed bias circuit, and then if it is that Q point must be fixed in the active region, then the circuit is good for amplification. Otherwise, we need to provide some guard circuit, some provide some compensation, some circuits to maintain the circuit operated in active region. So how to find for this particular fixed bias circuit a load line and a Q point? If you take this circuit, the circuit also treated as separating this VCC to RC and RB. So it is just like a, if you take separate same VCC in separate diagram, VCC, RB, VBE, ground. It is a loop. Supply, IARE, IRB, VBE, ground. So it is like a one loop input side. Another loop, VCC, ICRC, VCE, 0. This is another loop. So in this we have a two loops. So in order to get this, in order to get Q point, there is some procedure to follow. To obtain the Q point, apply the Kirchhoff voltage law to the input loop. What is the idea actually? So it is a circuit. We have given only circuit, given by circuit, fixed by a circuit. We don't have this characteristic graph. So from the mathematical analysis, we can get the Q point. So Q point is nothing but ICQ, VCEQ. So if you want to find out IC for this particular diagram, we need IC is equal to beta IB. So we have IB. Where is IB? Input side. How to get input side? Apply the Kirchhoff current law at Kirchhoff voltage law at input side. So we follow those steps. Then apply the Kirchhoff voltage law in the input loop of the circuit to get the ICQ. So apply Kirchhoff voltage law output side to get the VCQ. These 2 points nothing but Q point. So take the input Kirchhoff voltage law by seeing this diagram. So it is a loop in the network. According to network analysis, a positive supply start here. So VCC, the current flow in the RB nothing but IB, RB, voltage drop between base to emitter VBE 0. So that can be written plus VCC, IB RB minus VB is equal to 0. From this equation, we can extract IB. IB is equal to VCC minus VBE by RB. So from this equation, VCC minus VBE by RB. Once we know the IB, then each transistor having its beta current gain. So here common emitter current gain beta. So once we have the beta and IB from the input Kirchhoff voltage law, we can get IC is equal to beta IB. That is called ICQ. This equation is helpful for finding Q point for the problems given for the fixed bias. So ICQ is equal to beta IB. From the output loop, what is the output loop here? In this diagram, output loop means VCC, positive VCC, current flow in the RC, and then VCE, we have a VCE, and then 0. So we will get plus VCC minus ICRC minus VC is equal to 0. In this equation, VC is equal to VCC minus ICRC. So if we take that VC term right side. So VC is equal to VCC minus ICRC. VCQ is equal to VCC minus ICRC. So whenever the problem is given for this fixed bias, definitely they have given VCC. What is constant VCC? And then RC is a constant resistor. IC already we found just before this output Kirchhoff voltage law, we applied Kirchhoff voltage law at input side. So we can get IC is equal to beta IB. Once we know the VCQ, ICQ, we can get the Q point on the characteristic graph. So if you take the load line and Q point, if you in this diagram, what is Q load line for this equation? VC is equal to VCC minus ICRC. If you take the diagram, This is graph represents the VCE. This is the graph represents the IC in milliampere. What is the maximum extreme point in the VCE graph? Substitute IC y-axis 0.0, you will get VCC. So that is called VCC. And then the saturation point will get VC0, will get VCC by 2. VCC by 2 means VCC by RC. Here, substitute VC is equal to 0, IC is equal to VCC by RC. You can join these 2 points. This is called load line. And the Q point will take ICQ, comma VCQ. For fixed bias, ICQ nothing but beta AB, VCQ nothing but VCC minus ICRC. Suppose if beta changes, beta is the parameter for current gain for each transistor. No single transistor having same beta. So beta varies with each and every transistor. When ICQ is equal to beta IB, beta changes from 50 to some 100 or some 70. Then ICQ parameter changes. This ICQ parameter changes to, in this area, you will get the Q point changes. So you got to use this analysis. You will get this Q point, this one. Then VCQ is this place. Then the Q point is placed this one. Then whatever the, for example, it is a center signal, you will get the amplified signal like this. Whenever this Q point is moving, you will get the, you will draw the line here. Whatever the area in the saturation region, for example, it is a saturation region. So this saturation region, it is near to saturation. So you will get the clipping of the positive and the negative signal. So in order to avoid this, the variation in the beta, if you see here, the Q point is depends on beta. ICQ depends on beta. And also VCQ depends on VCC minus ICRC. IC depends on beta. So in order to get this Q point for this fixed bias, which depends on the beta, beta is depends on temperature. So actually these are interrelated. When temperature increases, IC0 increases, reverse saturation current increases. When IC0 increases, collector current increases. Collector current increases, which will make the more heat generated in the transistor, so that it will leads to again temperature increases. This cycle is repeat and going on in just like a circle. So that it will be unstable. The circuit is unstable. So beta is also functions of temperature. When beta changes, temperature changes, beta is also changes. When beta changes, IC changes. IC changes, Q point is moved up direction or down direction. This direction. So we'll get the Q point maybe this direction or this direction, that maybe moves from this point to this point. This is the reference point. So which may move up and down, so that you will get unfaithful amplification. How to stop that depends on beta. So we have another important circuit, important load line circuit, biasing circuit called voltage divider bias. In this voltage divider bias, same we have a transistor, common emitter configuration, connected with the biasing, proper providing supply voltages like VCC single source, RC resistor. This is RC resistor, this is R1 resistor, this is R2 resistor. When we connect, output is as it is, like RC, and extra we can add RE emitter resistor. Then In previous case, fixed bias, no R2 resistor. When we connecting R1, the biasing current flow through the R1 will get the voltage developed across this base point, which will make the transistor gets on. But in this case, when we use the two resistors in parallel, R1 is upside and R2 is connected from base to ground. It is like a voltage division rule. The two resistors are connected in voltage division rule. So when it is like a loop, VCC R1, I into R1, I into R2 and current, then these two are connected as a voltage division rule. Then what is the voltage drop across R2 means that will make the transistor gets on. When this R2 voltage across R2 means apply the voltage division rule, total voltage into R2 by R1 plus R2, you will get a voltage drop across this point. That voltage make this transistor gets on. So such type of circuit, this type of circuit is called voltage divider bias. So the voltage is division here. Some voltage drop here, some remaining drop here. That division in the voltage is called voltage divider bias. This kind of voltage divider bias providing to the transistor amplifier, we can achieve the circuit is stable and the circuit is independent of beta, so that whenever temperature changes, inside the circuit not that much of value changes, won't change, and the Q point must maintain fixed in the active region. So here, in order to get Q point for this voltage divider bias, we can't get the input Kirchhoff voltage law for this voltage division circuit. So instead we go with the Thevenin's equivalent diagram, Thevenin's theorem. The Thevenin's theorem, a network can be minimized into single voltage source in series with a resistor. So here one part is this transistor part, another part is voltage division part. This voltage division part can be minimized into single voltage source and in series with resistor, so that we can apply a Kirchhoff voltage law at input side. The resultant diagram for this input R1, VCC R1, R2, we can see here. So there are two current paths between point A and ground, one through R2, another through base emitter junction of the transistor here. So when base terminal having microampere current, total current here, division of this IB and I2, definitely these two are in parallel. So Thevenin's theorem applied to voltage divider bias. So if replace this diagram, divide that VCC for provide the R1, take that same VCC2 separate. So they are in like a voltage division rule. What is the voltage across R2 means? So here, actually, how to apply the Thevenin's theorem. The Thevenin's theorem says that Thevenin's theorem states that this is the network, for example. In this network, in order to get Thevenin's theorem, we have to provide Thevenin's voltage from this point A. So how to get VTH? VTH is nothing but what is the total voltage VCC into, if you want to find out Thevenin's voltage here, so that resistor is called R2 divided by total resistance is R1 plus R2. This can be get this VTH. Then what is RTH? The RTH can be achieved for this left side equation. If we want to measure looking into this Thevenin's network, and by providing short circuit of VCC, by providing short circuit for voltage source and open circuit for current source. If it is current source, open circuit. If it is voltage source, short circuit. Short circuit means we are providing, if it is ground, so this ground both are connected to same, so short. If it is short circuited, these two are, how can we find out from these two? These two are in which connection these two resistors? if point A measure the total resistance between these 2 points, so they are in parallel. Just like two elements, these two resistors are joined one side. Same resistor other ends are also joined the same place, other place. So they are in parallel. So these two resistors are in parallel, just like this one. Okay. Two resistors of one end. This is on one resistor, the other end joined common point, and other ends of the two resistors are also joined other common point. So then they are said to be in parallel. So when we look into that network, and by shortening the DC voltage and opening the open circuit of AC current source, then measure the total resistance. They are two in parallel. So RTH is equal to R1 R2 by R1 plus R2. We can replace this entire network with a simple VTH, nothing but which is equal to this one, and RTH which is equal to R1 parallel R2, R1 R2 by R1 plus R2, so that we can apply now Kirchhoff voltage law or Kirchhoff current law. Kirchhoff voltage law to the input side. Once we have applied the Kirchhoff voltage law to the input side, we get a IB. Once we know the IB, IC is equal to beta IB, and which is nothing but Q point, y-axis point. Then apply the Kirchhoff voltage law at output side. This is the loop. We can get the VC. So apply Kirchhoff voltage law input side. When we apply the Kirchhoff voltage input side, VTH minus IBRB, one drop between base to emitter, and IARE. This is the drop. So likewise, we can get the Kirchhoff voltage law. VTH minus IBRB, nothing but VRTH, VBE, VRE. VTH, VRB, VBE, IARE, nothing but VRE. So substitute Ohm's law, we can get VTH is equal to, take this variables on right side. VRTH nothing but IB into RTH, VBE take as it is VBE, IARE nothing but VRE nothing but IE into RE. And in this equation, when we substitute this IE term in terms of IB, because our aim is we can apply Kirchhoff voltage at input side is get IB term. So I is equal to 1 plus beta times of IB, because I is equal to IC plus IB, IC is replaced with beta IB, we'll get 1 plus beta times of IB. So 1 plus beta times of IB into RE. So when then RB extract the IB is equal to VTH minus VBE by RTH and 1 plus beta times of RE. We can take here. Take the IB term here. IB common this thing. So IB is common RE plus RTH. 1 plus beta times of RE plus RTH. So this is the IB equation. Once we know the IB, IC is equal to IC or ICQ is equal to beta IB. So beta we have for this circuit, and IB this equation. So this is the equation for IB, and multiplied by beta DC load line. We can get the DC Q point, one of the point. Then apply the Kirchhoff voltage law at output side. We'll get VCQ is equal to VCC minus ICRC. We have another extra resistor here. So IE into RE. Minus IERE. So which is approximately equal to VCC minus RC plus RE into ICQ. So when here, this is the VCQ point, this is the ICQ point. So joining of these 2 points is nothing but load line. So Q point is for the voltage divided bias is equal to VCC minus VCCQ, comma ICQ. So in the next lecture, we'll see that how this voltage divided bias is independent of beta, and then do with some problem so that we can get the what is the Q point and what is the load line for a given problem, like voltage divided bias circuit and fixed bias circuit.
Like, share and subscribe. Hit the bell icon for more updates.